Hello, am I audible?
Yes, sir.
Good
Okay.
evening, sir.
So we will wait for 2 minutes, then we will start. So let's start. Today we will discuss about thermodynamics. So let's first solve one problem.
Hello everyone. In this video, I shall discuss problem number 63 of GATE Physics 2022. This is a numerical answer type question. In this question, we have to find out the ratio of the change of entropies for 1 mole of nitrogen gas in processes 1 and 2. In process 1, the gas is held at 1 atm and is cooled from 300 Kelvin to 77 Kelvin, and in process 2 the gas is liquefied at 77 Kelvin. So let's solve this question. First we'll focus on process 1. In process 1 the gas is held at 1 atm pressure. So the pressure of the gas is constant during this process. So the change of pressure is 0 in this process. So dp equal to 0. The change of entropy in this process is given by integral dq by t. Now dq is equal to du plus p dv, where du is the change of internal energy, p is the pressure, and dv is the change of volume. This du can also be written as cv dt. Where cv is the specific heat at constant volume and dt is the change of temperature. For 1 mole of ideal gas, we have Pv equal to RT, where R is the universal gas constant. So let's take differentiation on both sides of this equation. So we have PdV plus VdP equal to RdT. As pressure is constant during this process, we have dP equal to 0. So PdV equal to RdT. Now we'll replace PdV by RdT in this expression. Here the limits of the temperature are Ti and Tf, where Ti is the initial temperature and Tf is the final temperature. In this question, Ti is 300 Kelvin and Tf is 77 Kelvin. For 1 mole of ideal gas, we have Cp minus Cv equal to R, where Cp is the specific heat at constant pressure. So we replace Cv plus R by Cp. As Cp is independent of temperature, we take it outside the integral. After integrating, we get Cp log Tf by Ti. So this is the change of entropy in process 1. In this question, Cp is given as 7 calorie mole inverse Kelvin inverse. So the change of entropy in process 1 is equal to 7 log 77 by 300 calorie Kelvin inverse. After calculating, we get change of entropy in process 1 as minus 9.52 calorie Kelvin inverse. It is interesting to note here that the entropy decreases in this process. Now let's focus on process 2. In process 2, the gas is liquefied at 77 Kelvin. We know that in a liquefaction process, the temperature remains constant during the liquefaction. So here the temperature Tf is constant during the liquefaction process, where Tf is 77 Kelvin. And dq is equal to minus L. Because latent heat is released by the gas in liquefaction process. So entropy decreases in this process, where L is given by 1293.6 calorie mole inverse. So change of entropy in process 2 is equal to minus 1293.6 by 77 calorie Kelvin inverse. After calculating, we get minus 16.80 calorie Kelvin inverse. Now we'll find the ratio of the change of entropies in process 1 and process 2. After some calculation, we get the ratio as 0.57. But we need to write down the answer after rounding off to 1 decimal place. So after rounding off to 1 decimal place, we have 0.6. So the ratio of the change of entropies in process 1 and process 2 is 0.6. So in this question the answer is 0.6. So 0.6 is the correct answer. Thank you.
Any question or doubt from this?
Sir, why we take m is equal to 1?
Sorry,
Mass
mass.
q is equal to
No, mass is not taken equal to 1 anywhere. Anywhere.
Sir, we took q is equal to ml for ld.
In which part? In first part or second part?
In second part.
Second part. Okay.
Yes, sir.
First part is clear, right?
Yes, sir.
Okay. What is your question in the second part?
We took q, delta q is equal to minus l.
Right. Why? Right. So
Yes.
here, see the question here. The latent heat is given for 1 mole of gas, right?
Yes.
And what is the amount? What is the number of moles of this gas? 1 mole, right?
One.
So
Mm.
if you multiply with it the number of moles, then it will be same, right? Because n equal to 1, small n. So
Yes,
I
sir.
mean this, I think I can write here. No, sorry, just give me 1 minute. Okay, so what is the total latent heat? Am I audible, right?
Yes, sir.
Okay, so so L prime is the total latent heat required, right? Or released.
Yes, sir.
Let's take mod here. Okay, the magnitude. What is this n? N is the number of moles. Okay, and this L is the latent heat for 1 mole. This latent heat for 1 mole is given here, right?
Yes, sir.
And in this problem we have it is mentioned that n equal to 1, so L prime is equal to L, nothing else. Simple. Clear?
Yes, sir.
Okay, fine. Any other question?
No, sir.
No. Okay,
Mm.
so there is no other question, right?
Yes, sir.
Okay, so let's solve another problem, similar problem on entropy.
Hello everyone. In this video I shall discuss problem number 37 of GATE Physics. (2022). This is a multiple choice question. Water at 300 Kelvin can be brought to 320 Kelvin using one of these following processes. In process 1, the water is brought in equilibrium with a reservoir at 320 Kelvin directly. In process 2, the water is first brought in equilibrium with the reservoir at 310 Kelvin and then with the reservoir at 320 Kelvin. In process 3, the water is first brought in equilibrium with the reservoir at 350 Kelvin and then with the reservoir at 320 Kelvin. The corresponding changes in the entropy of the universe for these processes are delta S1, delta S2 and delta S3 respectively. We have to find out the correct order of the change of entropies of the universe for these processes. So let's solve this problem. We shall first focus on process 1. In process 1, water is brought in equilibrium with the reservoir at 320 Kelvin directly. So the initial temperature of the water is 300 Kelvin and the final temperature is 320 Kelvin. The change of entropy of water in this process is equal to integral del Q by T. Here del Q is equal to C dt, where C is the heat capacity of the water. Replacing del Q by C dt, we get this equation. After integrating it, we get the change of entropy of the water is equal to C times log Tf by Ti. Here Tf is equal to 320 Kelvin and Ti is equal to 300 Kelvin. So this is the change of entropy of the water in process 1. Now the change of entropy of the reservoir is given by minus delta Q by Tf. This minus sign indicates that heat is released by the reservoir. So the entropy of the reservoir decreases. Here delta Q is equal to C times integral dt, where limits of the integration are Ti and Tf. So delta Q is equal to C times Tf minus Ti. So delta SR is equal to minus C by Tf into Tf minus Ti. Putting Tf equal to 320 Kelvin and Ti equal to 300 Kelvin, we get change of entropy of the reservoir is equal to minus C by 16. So the total change of entropy of the universe in process 1 is equal to delta SW plus delta SR, which is equal to C log 320 by 300 minus C by 16. Now let's consider process 2. In process 2, water is first brought in equilibrium with the reservoir at 310 Kelvin and then with the reservoir at 320 Kelvin. So there are two sub processes in process 2. For the first sub process, we have the initial temperature of water 300 Kelvin and the final temperature of water 310 Kelvin. So the change of entropy of water in A equal to C log 310 by 300. The change of entropy of the reservoir in subprocess A is equal to minus C by Tf into Tf minus Ti. Here the minus sign indicates that heat is released by the reservoir. Putting Tf equal to 310 Kelvin and Ti equal to 300 Kelvin, we get the change of entropy of the reservoir in subprocess A is equal to minus C by 31. Now let's focus on subprocess B. Here the initial temperature of water is 310 Kelvin and the final temperature of water is 320 Kelvin. So the change of entropy of water in subprocess B is equal to C log 320 by 310. The change of entropy of the reservoir in subprocess B is equal to minus C by Tf into Tf minus Ti. Putting Tf equal to 320 Kelvin and Ti equal to 310 Kelvin, we get the change of entropy of the reservoir in subprocess B is equal to minus C by 32. So the change of entropy of water in process 2 is equal to the change of entropy of water in sub-process A plus the change of entropy of water in sub-process B. Putting the values of the change of entropies of water in sub-process A and sub-process B, and after doing some simplification, we finally get the change of entropy of water in process 2 is equal to C log 320 by 300. The change of entropy of the reservoir in process 2 is equal to the change of entropy of reservoir in sub-process A plus the change of entropy of the reservoir in sub-process B. So the change of entropy of the reservoirs in process 2 is equal to minus C by 31 minus C by 32. So the total change of entropy of the universe is equal to delta SW2 plus delta SR2. So the total change of entropy of the universe in process 2 is equal to C log 320 by 300 minus C into 1 by 31 plus 1 by 32. Now we'll focus on process 3. In process 3, water is first brought in equilibrium with the reservoir at 350 Kelvin and then with the reservoir at 320 Kelvin. In process 3, there are two sub-processes C and D. In the first sub-process C, we have the initial temperature of water 300 Kelvin and the final temperature 350 Kelvin. So the change of entropy of water in sub-process C is equal to C log 350 by 300. The change of entropy of the reservoir in sub-process C is equal to minus C into Tf minus Ti by Tf. Putting Ti equal to 300 Kelvin and Tf equal to 350 Kelvin, we get minus C by 7. Now let's consider another sub-process D, in which the initial temperature of water is 350 Kelvin and the final temperature of water is 320 Kelvin. The change of entropy of water in sub-process D equal to C log 320 by 350. The change of entropy of the reservoir in sub-process D equal to delta QD by TF. Here delta QD is positive as heat is absorbed by the reservoir, as the reservoir is at lower temperature compared to the initial temperature of water. The amount of heat absorbed by the reservoir is equal to C into Ti minus Tf. So the change of entropy of the reservoir in sub-process D equal to C into Ti minus Tf by Tf. Putting Ti equal to 350 Kelvin and Tf equal to 320 Kelvin, we get the change of entropy of the reservoir in sub-process D equal to 3C by 32. So the change of entropy of the universe in process 3 is equal to the change of entropy of water in sub-process C plus the change of entropy of water in sub-process D plus the change of entropy of the reservoir in sub-process C plus the change of entropy of the reservoir in sub-process D. Putting the values of these quantities and after doing some simplification, we get delta S3 equal to C log 320 by 300 plus C into minus 1 by 7 plus 3 by 32. The second term gives minus 11C by 7 into 32 after some simplification. So the change of entropy of the universe in process 1 is equal to C log 320 by 300 minus C by 16, which can be written as C log 320 by 300 minus C into 1 by 32 plus 1 by 32. The change of entropy in process 2 is equal to C log 320 by 300 minus C into 1 by 31 plus 1 by 32. We have 1 by 31 greater than 1 by 32. So C into 1 by 31 plus 1 by 32 is greater than C into 1 by 32 plus 1 by 32. Multiplying both sides with minus 1, we get minus C into 1 by 31 plus 1 by 32 is less than minus C into 1 by 32 plus 1 by 32. So the second term in process 2 is smaller than the second term in process 1, and the first terms in both the processes are equal. So delta S2 is smaller than delta S1. In process 3, we have delta S3 equal to C log 320 by 300 minus 11C by 7 into 32. 11 by 7 into 32 can be written as 11 by 14 into 1 by 16, which is smaller than 1 over 16, as 11 by 14 is less than 1. So 11c by 7 into 32 is less than c by 16, or minus 11c by 7 into 32 is greater than minus c by 16. So the second term in delta S3 is greater than the second term in delta S1, and the first term in both delta S1 and delta S3 are equal. So we have delta S3 greater than delta S1, and we have found before that delta S1 is greater than delta S2. So finally we have delta S3 greater than delta S1 greater than delta S2. This is the correct order of the change of entropies in three processes. So option B is correct. So in this question, option B is correct.
Any question? Hello, am I audible?
Yes, sir. No, sir.
No question. Okay. Anyone else? No question, I think. So let's solve another problem.
Hello everyone. In this video, I shall discuss problem number 38 of GATE Physics 2020. This is a multiple choice question. The internal energy U of a system is given by U equal to lambda v to the power minus 2 by 3 a square, where lambda is a constant of appropriate dimension. V and S denote the volume and entropy respectively. We have to find out the correct equation of state of the system. Let's solve this question. From the laws of thermodynamics, we know that U is given by TdS minus PdV. So del U del S at constant V is equal to T. Similarly, del U del V at constant S is equal to minus P. In this question, we have U equal to lambda v to the power minus 2 by 3 square. So del U del V at constant S is equal to minus 2 by 3 lambda v to the power minus 5 by 3 square. Also, del U del S at constant V is equal to 2 lambda v to the power minus 2 by 3 S. Now, from these two equations, we have del U del S at constant V is equal to T, and del U del V at constant S is equal to minus P. So this is equal to minus P and this is equal to T. From the second equation, we have S equal to T by 2 lambda V to the power 2 by 3. From the first equation, we have P equal to 2 by 3 lambda b to the power minus 5 by 3 a square. Here we will replace s by t by 2 lambda b to the power 2 by 3. Then we get P equal to b to the power minus 1 by 3 t square into 1 over 6 lambda. So P b to the power 1 by 3 by t square is equal to 1 over 6 lambda, which is equal to a constant, as lambda is a constant. So P b to the power 1 by 3 by t square equal to constant. This is the correct answer. So option A is correct. Option A is correct.
Any question?
No, sir.
If there is no question, then we'll continue our discussion on canonical ensemble as we are doing last week. So let's continue the discussion now. I am sharing the screen. Okay. So in the last class, we have shown that the probability of finding some energy Es for a system in equilibrium with reservoir at temperature T equal to 1 by kb beta is given by this. This is called the probability of canonical distribution. From this, I will show that f equal to minus kbt log z. And what is this f? F is the Helmholtz free energy. And this z is called canonical partition function, which is equal to sum over s e to the power minus beta es. Now let's calculate the entropy first. What is entropy? Entropy is given by minus sum over s ps log ps. Okay. Here I will replace ps equal to this e to the power minus beta es by z. Here I will use the property of this logarithm function, which is this. Here I am using log a by b equal to log a minus log b. Now what is log of exponential of this thing? This is equal to minus beta es. So a is equal to minus beta by z e to the power minus beta es into s, where there is a summation over s minus log z by z into sum over s e to the power minus beta es. Now see here, sum over s e to the power minus beta es is equal to z, the canonical partition function. So from the second term we will get minus log z, because z and z will cancel out in the numerator and the denominator. Okay, so as z equal to e to the sum over s e to the power minus beta es, we have is equal to minus beta by z sum over s es e to the power minus beta es minus log z. Now let's consider one observable a. Now what is the expectation value or the average ensemble average of this quantity? Ensemble average of this quantity, this is equal to as sum over s as into ps. And for canonical ensemble we know that ps equal to e to the power minus beta es by z. So this is the ensemble average of this quantity a. So average energy, average internal energy will be equal to this. Okay, and in the first term we will replace 1 by z sum over s es e to the power minus beta es by this quantity, average of this energy, internal energy. So we have in the expression of entropy there was a minus sign here, right? S equal to minus of this quantity, so here will be minus, here will be minus sign, and this will be plus. So this will be plus and this will be also plus. This will be plus plus. So this is equal to this thing. Now let's also consider that S equal to, this is actually S by KB equal to this thing, equal to minus sum over S PS log PS. Okay, so this will be S by KB So S by KB equal to the average of internal energy by KBT with minus sign here plus log Z. Now multiply both sides with KBT. So we get TS equal to this will be plus, I think. So this will be plus. Okay. TS equal to average value of E plus KBT log Z. So E minus TS equal to minus KBT log Z. Now what is this? Internal energy minus T into S, where S is entropy and T is temperature. This is called Helmholtz free energy, as I have defined in the first class. Okay, so F equal to minus KBT log Z. So we have also derived this expression. Okay. Any question or doubt here?
No, sir.
Okay. Here, see, I have used one expression that S equal to minus KB summation S PS log PS. Okay. Last day I also used another expression KB log omega. Now what is omega? Omega is the number of microstates corresponding to a particular macrostate. Okay, so are they equivalent, these two entropy? Let's say this is entropy 1, this is entropy 2. Are they equivalent or not? Anyone knows this answer? Any idea?
No, sir.
No.
No.
Should I prove this or show in some way? Okay, let's show this. Okay, let's consider spin particles. Okay, spin, there are n spins. Okay, they may be spin up or maybe spin down. So in up is the number of particles with spin up, and in down is the number of particles with spin down, and this n is the total number of spins. Okay, so n up plus n down equal to n. Now what is this omega? In this case, omega will be the number of microstates will be n factorial by
N1.
right. This is right, correct? Okay, because there are total n particles, they can be organized in n factorial number of ways, and among them there will be in up how many in up there will be spin up particles, how many of them? There will be in up number of spin up particles, and there will be in down number of spin down particles. Okay, so this is the number of microstates. Okay, now what is entropy defined from this number of microstates? Entropy is defined as log of
N omega.
right. So let's put this omega equal to this here, then we'll get this thing. Right?
Yes, sir.
Okay. Now here we'll assume that this n is very large. Okay, this n is large, so this n up and n down are also large. Okay, we'll assume that are much larger than 1. Okay, then 1. So in this large n limit, we'll have something called Stirling approximation.
Okay.
All of you know that, right? The Stirling
Yes, sir.
approximation. Yes,
N ln
right.
minus n.
This is the Stirling approximation, right?
Okay.
Okay. Here we'll use this approximation in 3 of them. Okay, log n factorial, log n up factorial, and log n down factorial. Okay. So what will you get? So we get this expression here. N up plus n down is equal to n, so this and this cancel out. Okay, as n up plus n down equal to n. Okay, now this n can be written as this, n up plus n down. So n up log n plus n down log n minus n up log n up minus n down log and down. Now let's take this outside. I will take this n up common, and then I will get log n up minus log n, which is equal to log n up by n, plus similarly for down. Is this step clear to everyone? Hello? Is it clear to everyone?
Yes, sir.
Okay. So we get this thing. So there are total n number of particles, and among them n up are up spins. Okay, so the probability of finding spin up particle is equal to this thing, and p down is equal to this. And as you know, the sum of all the probabilities is equal to 1. You can also show it from this: p up plus p down equal to 1. Now I'll put this n up by n by p up, and I will replace n down by n by this thing, p down. So we'll get minus n kb, sorry, p up log p up plus so S by n, or the entropy per particle or entropy per unit particle, is equal to this. Okay, so we have started from the definition is equal to kb log omega, and we have arrived at is equal to minus kb sum over pi log pi, and here we have s by n because we are considering the entropy of per unit particle. Okay, here we are considering entropy per unit particle, or the canonical partition function was also for single particle canonical partition function, or this partition function is called single particle canonical partition function. If there are many particles, let's say n particles, then it will be like this. If the particles are indistinguishable, then there will be 1 over n factorial. I have discussed this 1 over n factorial in the previous class, I think. Okay, so let's stop here today. Now I want to know one thing from you. I was planning to have a discussion on Fermi-Dirac distribution and Bose-Einstein distribution next week. In any other class, are you discussing this thing?
No, sir.
No. Okay. Then we'll discuss Fermi-Dirac distribution and Bose-Einstein distribution next week. Okay. So let's stop here today. We'll continue next week.
Thank you, sir.
Thank you everyone for
Thank you,
joining.
sir.
Okay.
Thank you, sir.